Hey Math 135, what's up? In this video we're going to be looking at some extra examples in section 3.3 where we look at graphical solutions for linear programming problems. Remember, these problems can get very nasty. They can be quite long, and so it's important that you are diligent with your work and that you understand how to work through each step of the process fairly efficiently. So when we have a linear programming problem, we think about them as consisting of primarily 4 steps. The first step, we want to find the feasible region. Take our system of constraints here, graph our system of constraints, and identify the feasible region that corresponds to that system of constraints. Then step 2, we want to identify the corner points of that feasible region. In step 3, that's where we're going to take our objective function and evaluate the objective function. I'm going to, I guess, abbreviate that OF at the corner points. And then the last step is identify the max or min that you're looking for. And I think these first 2 steps are the ones where it can be very easy to get bogged down. Remember, this is old news. These are old problems. Sketching a feasible region, identifying the corner points. Those are problems that we've done before. That's nothing new here. But it's also the part that takes the longest. Okay, so let's go ahead and do that here. I'm actually going to get rid of some of this work just so that it doesn't clutter up the work that I'm trying to do. Again, remember, it's also important in the context of quizzes and exams to try to organize your work as much as you can. Try to organize your work on the page as well as you can, so that in the event that you make mistakes, it's easy to identify the things that are the things that are correct. Okay, so we've got three difficult lines and 2 that aren't as difficult. Line 1, line 2, and line 3. So for line 1, now I'm going to do all these with the intercept method, even when the intercepts aren't nice. That's one of the things with the linear programming problems. Even when the intercepts are not nice, we can still get a good idea about what the shape of the feasible region and which intersections correspond to our corner points. We don't have to be perfect, we just have to be close enough. So for instance, on this first line, the corresponding line is x plus 2y is equal to 50. My x-intercept, actually the x-intercept and the y-intercept are both nice here. The x-intercept is the point 50, 0. If I set y equals 0, then x would be 50. And the y-intercept, when x is equal to 0, we would get y is 25. I don't want the y though. I'm going to find all these intercepts first so that I know the right scale for my picture here, my graph. All right, so that's the first line. The second line would be 5x plus 4y is equal to 145. The x-intercept is reasonably nice-ish. If I set y equal to 0, let's see, 5x would be 145. And 145 divided by 5 is 29. So the x-intercept here would be 29, 0. The y-intercept is not pleasant. When I set x equal to 0, I get 4y is equal to 145. And 145 divided by 4 is a decimal number, but again, we're just trying to get close enough. Our picture doesn't have to be perfect. 36.25. Okay, and then for the last challenging line, line 3, we get, let's see, 2x plus y is equal to 25. Here the x-intercept is unpleasant. It's 12.5. The y-intercept is relatively nice. Okay, so those are our intercepts. It looks along the x-axis, the furthest I have to go out is 50. So, all right, we'll make this 50 out here. And along the y-axis, I think the furthest we have to go out is 36.25. And so we might as well make this 50 up here as well. So then, let's see, that's 40, 30, 20, 10. And then here we've got 40, 30, 20, 10. And then there's our origin at 0, 0. Okay, so let's start to get some of these guys drawn in. That first line has an x-intercept of 50 and a y-intercept of 25. It's a reasonably straight line. So there's line 1. The second has an x-intercept of 29, 0. So, all right, just get kind of close to 30. Again, it doesn't have to be perfect. And a y-intercept of 36.25. So just a little bit above 35. I am on point right now with my lines. All right, there's the second line. And then line 3 has an x-intercept of 12.5, which is halfway in between 10 and 15, and a y-intercept of 25, so the same y-intercept there. It can be helpful here too to kind of mark these, because these intercepts might actually be interesting points. So this one was 36.25. This one was 29. This one's 12.5. So there's that third line. And then we have y equals 9 that we have to draw in. That's a horizontal line passing through 9 on the y-axis. I guess we could call that line 4. And then x equals 0 is the y-axis. Those are all the points where the x-coordinate is equal to 0. All right. Now when it comes to we got a bunch of different possible feasible regions here. We got to figure out which one we're looking at. So I guess on all of these lines except for the x, let's see, x is greater than 0. That means we got to be pointing into the right half plane. For the first line, if I test the origin, all these other lines, the origin's not on the line. So if I test the origin for the first line with the inequality, we get 0 is less than or equal to 50. That's true. So for line 1, here's this line, we got to be pointing back towards the origin. For line 2, when I test the origin for line 2, let's see, that gives me 0 is less than or equal to 145. That's also true. So line 2, we want to be pointing back towards the origin. for line 3 when I test the origin. Let's see, here's line 3 up here. We get 0 is greater than or equal to 25. That's false. So line 3, we want to be pointing away from the origin. So like right now between, I guess we are in between line 3 and line 2. There's a strip. There's a strip here between line 3 and line 2. I guess they'll eventually cross up here somewhere. We're in this strip right here. Below line 1. So I guess we're kind of here. Line 4, y is greater than 9. So if I plug in 0 for y there, when I test the origin, we get 0 is greater than 9, which is false. So for line 4, we also want to be pointing away from the origin. So it looks like our feasible region, I'll shade it in using a different color here. Our feasible region is this part right here. And we've got 4 corners for that feasible region. Go ahead and label them A, B, C, and D. Okay. So I think, let's see, D is going to be easy. D was one of these y-intercepts. D was the y-intercept for both line 1 and line 3. So D we know right away. Part of organizing your work here at the very end, we're going to make a t-chart when we go to do part 3 and 4, where we evaluate our objective function at these corner points. We usually use a t-chart with our corner points, x, y, and our objective function, 7x minus 5y. So we're going to have 4 corner points here, A, B, C, and D. And we've already got one of those. D is the point 0, 25. Okay. Now the other ones, I think we're going to have to maybe set up some systems of equations to solve these things. Corner point A, that's where, let's see, there's 2 lines crossing here. It looks like it's line 3 and line 4. Line 3 had the equation 2x plus y is equal to 25. And line 4 has the equation y is equal to 9. Okay. So that's easy enough. Let's see, we've already got the y value. We have 2x plus 9 is equal to 25. So 2x is 25 minus 9 is 16. I got to resist the temptation to like go fast here. Just you know, keep it at a nice even pace here. So we get x is equal to 8. So point A has coordinates 8, 9. Okay, let's see, point B. That looks like that's where line 2 and line 4 cross. So line 2 is 5x plus 4y is equal to 145. So again, corner point B is where line 2 and line 4 cross. Line 2 has the equation 5x plus 4y is equal to 145. And line 4 gives us our y coordinate. All right, so that one's not too bad either. Let's see, we have 5x plus 4 times 9 is equal to 145. So 5x is equal to 145 minus 36. 145 minus 36 is 109. And so x here would be 109 divided by 5. That's going to have a nice decimal, 21.8. Okay, so point B has coordinates 21.89. Then finally, point C, I think that's going to be the one that's most challenging. Point C is where line 2 and line 1 cross. We're just running up right to the edge of our space here. So C was where line 1 and line 2 cross. Line 2 has the equation 5x plus 4y is 145. And line 1, has the equation x plus 2y is equal to 50. All right then, I think if we multiply line 1 by 5, or maybe, sorry, by 2. I'm going to multiply it by 2. Multiply everything by 2. I'm going to make the y's match up. Or actually, I'll make it multiply by -2, so I can make the y's opposite. So negative 2x minus 4y is equal to negative 100. And then line 2, we're already good. 5x plus 4y is equal to 145. So when I add those two equations together, gives me 3x is equal to 45. So x will be 15. And then I'll use the first equation. 15 plus 2y is equal to 50. So 2y will be 35, which means y is 17.5. So we get the point 15, 17.5 for C. So notice we have some decimal answers here, so we don't want to get too spooked by that. We can also go look and make sure that the values that we found kind of correspond. Okay, yes, the point A looks like it could be 8, 9. And B, yeah, it's a little bit bigger than 20, and the y coordinate is actually equal to 9. C, the x coordinate of C looks like it should have been 10, and the y coordinate for C looks like it should be bigger than 20. And so that's a little bit, that's a little bit disconcerting. So I'm a little bit worried at this point that I made a mistake. So there, I might go back and check. Okay, did I make a mistake here? Did I make a mistake? I got equation, so point C was equation 2 and equation 1. Equation 1, x plus 2y is 50. X plus 2y is 50. Equation 2, 5x plus 4y is 145. So I copied down the equations right. When I multiplied this equation by negative 2x minus 4y, negative 100. So I did that correctly. I think I added there correctly. All right, so again, I was a little bit worried that my point here didn't match what I saw. So I did a quick check. I'm satisfied now after my check. Again, I'm not 100% certain, but I'm confident now to go ahead and move forward. So we're on to step 3 now. We've identified our corner points of our feasible region. We're on to step 3, where we're going to evaluate our objective function here, which means plug in 8 for x here and 9 for y. 7 times 8 minus 5 times 9. And this is, again, a point where you got to resist the temptation to be speedy. So that gives me 11. Let's see. 7 times 21.8. minus 5 times 9. Gives me 107.6. For point C, we're doing 7 times 15 minus 5 times 17.5. That gives me 17.5. And the last one will be 7 times 0 minus 5 times 25 is negative 125. Okay, there's step 3. That's the evaluate. And then the last is find the max or min. Well, we're looking for a max here. We're looking for a max here. So that would be, I guess, the biggest number on this list is 107.6. Okay, so F has a max of 107.6 at the point 21.89. Okay, so there's the first problem there. It took us about 20 minutes to get that done. Let's move on to problem 2. Solve the linear programming method by the method of corners. So we're going to do the same kind of stuff. Luckily here we've only got a couple of lines. Should switch back to the red. Line 1 and line 2. And I guess this is line 3. It's the only other interesting one. So just to get a sense for what our scale should be here, line 1 would be 3x plus 2y is equal to 12. That has an x-intercept of 4 and a y-intercept of 6. Line 2 would be x plus 2y is equal to 6. That has an x-intercept of 6 and a y-intercept of 3. And then I guess line 3, the line y equals 1, is a horizontal line. Okay, so we got a reasonably good scale on all these. All the intercepts are nice. So I think we can just use a normal scale here. So for the first line, we have an x-intercept of 4. 1, 2, 3, 4. An x-intercept of 4 and a y-intercept of 6. 1, 2, 3, 4, 5, 6. All right, there's line 1. Line 2 has an x-intercept of 6 and a y-intercept of 3. Line 3 is the horizontal line, y equals 1. So it's going to be a horizontal line passing through y equals 1. And x greater than or equal to 0, that's going to be our y-axis. So the line x equals 0 is our y-axis. Now when it comes to getting the inequality parts drawn, that x greater than 0 means we're going to be in the right half plane. For line 1, when I test the origin here, we get 0 is greater than or equal to 12, which is false. So line 1, we want to be pointing away from the origin. Line 2, when I test the origin, that gives 0 is greater than or equal to 6 is false. So line 2, also, we want to be pointing away from the origin. And then line 3, when I plug in the origin, I guess I just have to plug in 0 for y. I get 0 is greater than or equal to 1. That is false. And so line 3 is also going to be pointing away from the origin. And so I think the region that has all the arrows pointing into it, this is an unbounded region. I guess I'll stick with the red here. It's this region out here. Okay, we got that feasible region drawn. We can go ahead and start to identify the corner points. I think I see 3 corner points. Three corner points for this feasible region, A, B, and C. A looks like, hey, that's our y-intercept for the first line. So when we make our list of corner points, A is the point 0, 6. It's the y-intercept for that first line. B and C, we're maybe going to have to do a little bit of work to do. B, corner point B, looks like it's the intersection of line 1 and line 2. So line 1 has the equation 3x plus 2y is equal to 12. And line 2 has the equation x plus 2y is equal to 6. That's already set up for a nice elimination. If I just subtract, I get 2x is equal to 6. So that gives x equals 3. And then using the second equation, 3 plus 2y is equal to 6. So that would give 2y is equal to 3. So y is equal to 3/2, or 1.5. And that looks like a reasonable value for our point B here. If I had maybe drawn the lines a little bit better, we might have been able to guess that. So point B is 3, 1.5. Now point C here looks like it's on the intersection of line 2 and line 3. And since line 3 is a horizontal line, I think this one's going to be pretty easy to solve. Line 2 was x plus 2y is equal to 6, and line 3 is y is equal to 1. So we already got our y value. We have x plus 2 times 1 is equal to 6. So x will end up being 4. So C is the point 4, 1. All right, we were able to make relatively short work of our corner points this time. So that's the end of step 2. Now into step 3, we have to evaluate our objective function at each of those 3 points. The objective function here is x plus 2y. So when I take 0, plug it in for x, plus 2 times 6, that gives 12. The next one, plug in 3 for x. 3 plus 2 times 1.5 would be 6. And then the last one, when I plug in 4 for x, 4 plus 2 times 1, that also gives 6. So there's actually two places where I get my min. So remember, on this one, we're looking to minimize. This expression. I think this is related to the fact that my objective function was also one of my lines. Okay, so we're looking to minimize. We found the smallest value. I guess we kind of did step 4 right away. So we have our cost function. C is minimized. at, let's see, 3, 1.5, and 4, 1. And if you remember, there's the second part of that fundamental theorem of linear programming, that it's actually every value along that line between those 2 points as well. But we're not too much worried about that. We're actually more interested. C has a minimum value of 6. All right, then. So that one went by much, much quicker than the first one. I think these problems are ones where the first few that you do when you're thinking about every step, it can take a while. But if you can graph these lines relatively quickly, if you can evaluate, test the origin or figure out how to get the inequalities sorted out efficiently, it's just really important to just have an efficient method. So the first couple so far, I've drawn all the lines first and then dealt with the inequalities. Maybe in the next few, I'll deal with the line and the inequality at the same time. Again, the important thing for you is that you find an efficient way to get through these problems without getting too hung up on things and without second guessing yourself. All right, let's move on to some story problems here. We get to practice setting these guys up. Number 3. Perth Mining Company operates 2 mines for the purpose of extracting gold and silver. The Saddle Mine costs $15,000 per day to operate, and it yields 50 ounces of gold and 3,000 ounces of silver each day. The Horseshoe Mine costs $19,000 per day to operate and yields 75 ounces of gold and 1,000 ounces of silver each day. Company management has set a target of at least 650 ounces of gold and 18,000 ounces of silver. How many days should each mine be operated so that the target can be met at minimum cost? What is the minimum cost? So our first job here is to get ourselves a linear programming problem. The first 2 problems that we worked on here in the video were just boring linear programming problems. Here we've got a story, and our first task is to translate that story into a boring linear programming problem. We have to identify and define our variables. So here, I guess our variables, we got how many days. How many days should we be operating? Should each mine be operating? So we got 2 different mines, and we got to figure out the number of days for each. All right, so we're going to let X be, okay, we got Saddle Mine, so number of days for Saddle Mine. And Y will be the number of days for the other mine, Horseshoe Mine. All right, so those are our variables. We have an objective function. We're trying to minimize cost here. So the cost of operating the mines. So we're trying to minimize our cost function. Let's see. It costs $15,000 a day to operate Saddle Mine. So 15,000 X plus 19,000 Y. If I operate the second mine for Y days, it's going to cost 19,000 Y to operate that mine. All right, so there's our objective function. Then our constraints here. Now, this is where, remember, it can be beneficial to, all right, before we even start to think about what our constraints are, let's think about, if I want to minimize this objective function, let's just not operate the mines at all. I guess we can't operate for a negative number of days, and so we're always going to have this first quadrant, these first quadrant constraints. But all right, if I want to minimize my cost, let's just not operate the mine. But we can't not operate the mine because we have to get a certain amount of gold and silver. All right, so we've got 650 ounces of gold and 18,000 ounces of silver that we need to mine. And so there's going to be two equations. There's going to be a minimum gold inequality, and a minimum silver inequality. Okay, so the amount of gold that we mine has to be at least 650 ounces. It says the first mine gets 50 ounces of gold a day, so it will, if it operates for X days, it will mine out 50X ounces of gold. The second mine, horseshoe mine, gets 75 ounces of gold a day. So if it operates for Y days, it will get 75Y ounces of gold. And the silver inequality is very similar. We have to get at least 18,000 ounces of silver. Let's see, saddle mine gets 3,000 ounces a day. So we've got 3,000 X is the amount of silver that saddle mine will get if it operates for X days. And for horseshoe mine, it's 1,000 a day. So horseshoe mine will extract 1,000 Y ounces of silver over Y days. All right. And I think that incorporates just about all the information from our story. I've underlined all the numbers, and so I don't think there are any other constraints that we need to worry about here. All right, so we have our objective function and our system of constraints. And we want to use the method of corners to get the job done. So that means we need to graph our feasible region. So let's go ahead and copy down the boring linear programming problem here. Minimize this cost function, 15,000x plus 19,000y, subject to. Now I'm going to take this opportunity to simplify a couple of these constraints. So for example, everything in the first inequality is divisible by 5. Actually, it's divisible by 25. Everything there is divisible by 25. So if I divide everything in this first inequality here by 25, we get 2x plus 3y is greater than or equal to 650 divided by 25 is 26. Everything in the second inequality is divisible by 1,000. So if I take the silver inequality here and divide everything by 1,000, that gives me 3x plus y is greater than or equal to 18. And then we've got those last two constraints that are just saying, hey, we're in the first quadrant here. Okay, so we're going to graph our feasible region. I think there's only two lines that are interesting here, line 1 and line 2. So line 1 is 2x plus 3y is equal to 26. It has an x-intercept of 13 and a y-intercept of, let's see, 26 divided by 3. It's not going to be a pleasant number, 8.67. But again, remember, when it comes to identifying graphing our feasible region and identifying the corner points, we just need a good enough. We don't need a perfect picture. We just need one that's good enough. Line 2 is 3x plus y is equal to 18. Oh, I said I was going to graph these guys one at a time and look at their... I got to get the... I guess before I graph them, I have to figure out what my scale is going to be. The x-intercept for the second one is going to be 6, 0. And the y-intercept would be 18, 0, 18. So it looks like I'm going up to 13 on the x-axis, sorry, out to 13 on the x-axis, and up to 18 on the y-axis. So maybe I should just go by 2s. Maybe I should just go by 2s. So we got 2, 4, 6, 8, 10, 12, 14 is as far as I have to go out there. And 2, 4, 6, 8, 10, 12, 14, 16, 18 is as far as I got to go there. Okay, so for this first line, we have an x-intercept of 13. It's right there. And a y-intercept of 8.67, which would be not quite halfway up there. And there's my line there. That was the worst one yet. Line 1. And if we test the origin here, we get, let's see, 0 from looking at this inequality here. Plug in 0 for x and y. I get 0 is greater than 26, which is false. So we want to be pointing away from the origin. And the second line has an x-intercept of 6 and a y-intercept of 18. So there's my line 2. And if I test the origin here, that line was disgusting. Let's see. I get 0 is greater than or equal to 18, which is false. So this one we also want to be pointing away from the origin. Now we also have the x is positive. And so that means that we're in the right half plane. And the y is positive. So that means that we're in the upper half plane. So our feasible region here is going to be this guy. And there are 3 corner points, 2 of which are going to be very easy to identify. So if I label them A, B, and C, A and C are intercepts for these lines. So when we go to make our table, A is the point 0, 18. That was the y-intercept for the second line. B is the one that we're going to have to do a little bit of work for. C was the point 13, 0. That was the x-intercept for the first line. Okay, so B is where line 1 and line 2 cross. Line 1 was 2x plus 3y is equal to 26. And line 2 was 3x plus y is equal to 18. And now it looks like B might have been at the point 46. And so I guess maybe we could guess, is it the point 46? And that's where we could check. All right, 2 times 4 plus 3 times 6, that's 8 plus 18, that's 26. That checks out. And then, let's see, 3 times 4 plus 6, that's 12 plus 6, that's 18. That checks out too. Okay, so we successfully guessed. We successfully guessed that it was the 0.46. And for what it's worth, I don't have that sitting in front of me. I just guessed that. Like, I legitimately just now on the spot guessed that. So that's something that you can do. You can always guess, like, hey, maybe if I had drawn this line should have been a little bit lower, and this line actually looks like it goes right through 4, 6. So all right, I drew that line okay. But you can kind of guess those things. The important thing, and this is something I noticed on a quiz, is that when you guess and check, you're checking the equations. I think a lot of folks were checking the inequalities. You got to check the equations when you're guessing your corner points. All right, so we successfully guessed that corner point B, and we have our 3 corners now. We're ready to move on to phase 3, where we evaluate our objective function. In this case, it's 15,000x plus 19,000y. I genuinely was not expecting that guess to work out. Okay. And so if we plug in A, point A, 0 for x and 18 for y, so 15,000 times 0 plus 19,000 times 18. So our operating costs at that corner point are $342,000. So that's if we operate all out of that second saddle mine. Was that the second one saddle mine? Second was horseshoe mine. Okay. For the second point, we got a mixture here. So 15,000 times 4 plus 19,000 times 0. So, sorry, 19,000 times 6. Jumping ahead of myself here. 174,000. And the last one, if I plug in 13 for x and 0 for y, 195,000. So I guess that makes sense if we operate all out of the second one. I guess the corner point A means, all right, we're doing all of our mining at that second mine. That's the one that's more expensive to run. The first mine is less expensive to run, and so it makes sense that it would be, I guess, more cost efficient to run out of the first mine. But the mixture, I guess the idea that since they're both kind of good at different things. Looks like the first mine is good at getting silver, and the second mine is good at getting gold. Since they're both good at different things, then a mixture of the two will be the most cost efficient. So we're trying to minimize our costs here. And so I guess to answer the questions here, how many days should each mine be operated? What do we got here? Saddle and horseshoe. X is saddle, so 4 days at saddle mine, 6 days at horseshoe, and then the second part of the question here, what is the minimum cost? Okay, operating cost, minimum operating cost, operating costs of $174,000. Okay, so that'll do it for this example. This video looks like it's been going for about 50 minutes here, so we're going to go ahead and wrap these examples up in a second video. So I'll see you in part 2 of our linear programming problems examples.